a 3-level system with energy level values of E0 equals 0 kBt, E1 equals 2 kBt, and E2 equals 6 kBt. So assume energy levels have degeneracies of G0 equals 1, G1 equals 3, G2 equals 2. So the G stands for the degeneracy value, and the epsilon E stands for the energy level value. So we look at the first question. It says to calculate the partition function Q. And to do that is, here you can see that Q, to calculate the partition function, you take into consideration the number of degeneracies of the energy level. So as if you can recall, the degeneracies is how many equivalent energy levels or energy values per energy level. So here, G0 has 1. This is energy level 0. There's only one degeneracy. And at energy level 1, there is 3 degeneracies. And at energy level 3, there is 2 degeneracies. Or you can label it basically 2, because we started at 0, 1, 2. So to solve this, to calculate the partition function, you have to basically substitute in the numbers. So Q equals G0 e to the negative E0 kBt, and you take the sum of all of it. And then lastly is G2 e to the negative E2 over kBt. And if you plug in the values here, so Q, I should put more room. Q equals 1 plus 3 for the next degeneracy, e to the negative 2. The kBt cancels because there's kBt in the denominator. Plus 2e to the negative 6, which gives you a total partition function, which is a sum of 1.41. B, to calculate the probability of the particle found in ground state. To do that is you use this equation here in red, and to find the probability I, which is at any energy level, but here it's asking for ground state, what you do is you take the probability, and we want ground state, so that'd be 0, so G0 e to negative E0 over kBt, and then all over the partition function Q. And so what we get basically is 1 e to the 0, 1.41, which is equal to 0.709. And for the next problem, it asks for the probability that you find the particle with energy E1. So if you want to find the probability P1, to do that, you do this similarly. You do P1 equals G1 e to the negative E1 over kBt all over Q. And to calculate this, then again, as you can remember, we don't need the temperature value because kBt cancels, in case that throws you off. So G1 is 1 e to negative E1, which is 2 kBt, over kBt, which basically you cancel that out, all over the partition function of 1.41, which we already calculated. And that would give you, oh, wait, never mind. It's G1 is actually equal to 3, which would give you 0.288. Yeah, just make sure you substitute in the values correctly. And for the next problem, so it says to calculate the probability the particle has energy E2. So this one you find P2, this time probability you find the particle with energy E2. And to do that, basically do the same thing. And so what we get is 2 e to negative 6 because the kBt's cancel all over the partition function. And then you should get 0.00352. So once you calculate these probabilities, you could end up calculating the average particle energy. And to do that, it's U over Avogadro's number, which is equal to the sum of the average energy levels. The brackets indicate average, and which is the same thing as the sum of the probabilities times the energy states. And this is all at temperature of 1000 Kelvin. So to do that is, well, you take the sum of the energy levels, which is equal to P0 E0 plus P1 E1 plus P2 E2, and then you end up having 0.709 times 0 plus 0.288 times 2 kBt, and we already have T, which is 1,000 Kelvin, and then plus 0.00352 times 6 kBt. What you should end up with is 0 plus 7.95 times 10 negative 21 plus 2.9 times 10 negative 22, and you should end up with, is all in joules, you should end up with an energy of 8.24 times 10 negative 21 joules. And recall, we are calculating U over N, which is the same thing as the sum of the average of the energy levels. So that's what U over N is. And for the final problem, it says to calculate the particle entropy, S over Avogadro's number. To do that, we know that to calculate entropy, it's the internal energy, or temperature, plus Avogadro's number times Boltzmann constant times natural log of Q. And A times KB is technically R, and R is equal to 8.314 joules per mole Kelvin, so you could use that instead if you want. So to do that, is we substitute, we don't have U, so we can substitute U, which is equal to Avogadro's numbers times E, put that there, and then you'll have S over Na. So to calculate S over Na, to find the particle entropy, you take the average energy, which we already calculated, to be 8.24 times 10 negative 21 joules over temperature, which is 1,000 Kelvin, plus Kb, Boltzmann constant, 1.38 times 10 negative 23 joules per Kelvin, and times the natural log of Q, which is the partition function, which is 1.41, and you should end up with the average, which is the particle entropy, to be 1.30 times 10 to the negative 23 joules per Kelvin. So make sure the units are joules per Kelvin.